All right, in this lesson we're going to be talking about wave interference. So what exactly does that mean? Interference, maybe you've heard the word interference before, right? You're interfering with someone, you're getting in the way of something. So it kind of has to do with that, just really just relating to waves though. And in this GIF, uh, something this is an illustration or example of wave interference. Now, there are many ways you can describe what's happening in this GIF. For example, if you relate it to energy, as these kids are bouncing on the trampoline, they're adding elastic potential energy into the system. So they're increasing the elastic potential energy. And as they are increasing the energy, they are also increasing the energy that is transferred to this kid flying upwards. And so you can explain it using that method, right? You can use uh, that concept of energy, but we can also explain it using something using waves, right? And so we're gonna move on. I want to talk about waves, but before that, you really need to know what two terms are, and those two terms are called nodes and antinodes, right? So nodes Nodes are really just the thing in the middle. They're at the equilibrium point, right? So there's an equilibrium point in the middle in which this wave goes up and down, up and down. So the nodes are in the middle. And the antinodes are the one that are the farthest, what we describe as the farthest point from the equilibrium. So the maximum displacement from the equilibrium. So your antinode is the maximum displacement from the equilibrium point. So usually the antinodes are in the middle, right? So it's usually the highest point. The highest point right here, highest point right here, highest point right here. It's either here, here, or here. All right, so they're only at these points, only at these points. Not the antinodes aren't being referred to as the entire point in between this wave. Rather, they're just at the highest or the lowest point. So those are antinodes. I think that should be easy to understand. So nodes, they're at the equilibrium, and antinodes uh, are the points at which there is the greatest displacement. The greatest displacement. Now, we talked about this idea that waves don't transfer particles. If you remember, if you took a look at the GIF from the previous lesson videos, you'll see that, well, when the wave was moving, when the wave was moving, nothing else, the particles weren't moving. It was only the wave that was moving. And I guess I should uh, give you a reminder, right? Because maybe you probably don't remember. Right here. So if we take a look at this particle, right? If we take a look at this particle, this red dot, the particle itself is not moving. The wave is, right? If we take a look at the bottom right here, the wave is moving to the right. The wave is moving to the right, but the particle itself is not moving anywhere. It's just moving back and forth, back and forth. And so a wave does not transfer matter. A wave does not transfer matter. A wave transfers energy only. And so we're going to relate this point back to what we see here. Since a wave only transfers energy, it's a wave only transfers energy, you'll realize that the energy just goes past each other. They don't cancel each other out. Well, they do cancel each other out at a certain point, right? If we take a look at the middle, they're kind of combining, or rather, they're canceling out or combining. Oh, here. So see, they're combining at the middle, but then they're moving past each other like nothing ever happened. And now let's take a look at this part. right? So this one's on top, this one's on bottom. And you'll see that they combine and kind of cancel each other out as they go through the middle. So again, waves do not transfer matter. Waves transfer energy only, and this energy is undisturbed. This energy is undisturbed. Let's take a look at this in real life. And it happens just as we predict to happen in real life, albeit there's some sort of friction. Albeit some sort of friction. Again, this real world's not perfect, but you do see that the energy passes along pretty much undisturbed, right? There's a combination in the middle. There's a combination in the middle when these two waves interact, but there really isn't. But they don't cancel each other out as they move past each other. Okay, so that's a very key idea to remember. They might they might interact. They might interact at a certain point, but they're not going to destroy each other. That the energy continues moving on without being affected. But what happens in the middle, right? What happens in the middle? What happens in the middle when these two waves combine? So you kind of see a greater height. Well, if you combine these two waves, right, it's a little got a little bit higher, and we call that constructive interference. Isn't this a GIF? I think this is a GIF. Yeah, it is. It is a GIF. So you see, let's take a look at the yellow dot, right? The yellow dot, the black dot right here. We take these 2 points. They're gonna combine. If you combine these two waves, what's gonna happen is you're gonna get something we call constructive interference. You see that the amplitude of this wave is 1. Whatever unit it is, we don't know. But the amplitude of this wave at this point, this top wave, is 1 at this black dot. Or rather, there's no dot anymore. And the amplitude of this bottom wave is also at 1. Well, if you put this wave superimposed on this wave, you're going to have a combination of these two waves, right? 1 plus 1 is 2. 0.5 plus 0.5 is 1. 0 plus 0 is 0. -1 plus -1 gives you -2. Right? So if you have two waves that look just like each other, you're going to get something called constructive interference. All right? So that's how you would interpret this, right? And on the opposite end of the spectrum, you can get something called destructive interference. And take a look at these two waves. These two waves are completely different. Right? They're completely different from each other. Uh, This has an amplitude of 1 at this point, and this wave on the bottom has an amplitude of -1 at the same exact points. Well, what's going to happen is that, well, if you add 1 plus -1, you're going to get 0. You add 0 plus 0, you're going to get 0. And so when you put this wave superimposed on right on top of on this wave on the top, you're going to get a straight line, right? These two waves are going to destructively interfere. Now, that's not to say that the energy is canceling each other out, right? That doesn't mean that the energy is gone. It just means that, or rather, that's not a really good way to say it. It doesn't mean, forget what I said about energy canceling each other out. It doesn't mean that the energy is gone. The energy is still there. And if you were to somehow separate these two waves again, you would you would see that it would come out undisturbed. But when you combine these two waves, what you're gonna see is you're gonna see destructive interference. You're gonna see destructive interference. And again, this is the idea of wave superposition. The idea that two waves, when combined, there is a displacement when you combine those two waves. And so if you combine these two waves, as the waves combine, you see that they go from constructive to destructive interference. Right? That's what we call wave superposition. And so you don't need to know exactly what superposition means. You just need to know what superposition means in the context of constructive and destructive interference. So that's the only thing you need to understand. And so now we watch this video. Hopefully I don't get copyrighted.
I've got a demonstration here on a little pond where we can see this with water waves. I have two sources.
Oh, yeah. So what he's going to do is he's going to demonstrate the idea of constructive and destructive interference with water waves. That's what he's going to do.
I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference.
See these
But
lines
if the peak
in the middle,
from one wave...
These lines in the middle are the constructive the waves from each of these balls, each of these waves from these balls are adding to each other here. There's constructive interference here. So the waves are being combined here and they're going to go up to a higher height. And so these areas right here, here, that's an evidence of constructive interference.
Meets up with the trough from the other, then we get destructive interference and there's basically no wave there.
And destructive interference is occurring right here because again, you don't see any wave here, right? These small white lines are two ways in destructively interfering with each other. So you're gonna see no amplitude. It's just gonna be a flat line.
I've got a demonstration here on a little pond where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there.
So yeah, we see this happening in real life all the time. Right? A lot of things can be interpreted as a wave.
I've got a
So now let's go back to this GIF in the beginning. Well, what the four boys are doing when they push down the trampoline, they're creating this wave. Right? They're pushing down the trampoline and there's a wave being generated there. And when the kid in the middle goes up and then jumps back down, he's also creating a wave. The energy, which is the amplitude, right? The amplitude of a wave. The energy is the amplitude of a wave. Both the waves that the four boys are creating and the wave that the boy is creating when he when he falls down on a trampoline, that's an example of constructive interference. So the energy of the wave that the boy is generating in the middle as he falls down, and the waves that the four boys on the side, on the corners are generating, they both add up and creates an even larger wave with a much larger energy. And so the boy is able to jump up to a higher height every single time. I mean, but I would still explain this using the work energy term. I would still explain this using energy. But this is also another example of, well, how can you see waves occurring, right, in real life? So let's move on. Let's move on. This website right here is a example of Well, you can use it to uh look at waves. It's not this right here. This is something else. But this is another it's another simulation basically that you can play with. Let's see. Listening to single source, sure. So this is a single sound wave, and we talked about water waves before, but this is going to be a sound wave, right? So this is a sound wave. And now we have two sound waves, right? So just like the what you watched before, two water waves, we're going to think about it in terms of two sound waves. Now, if two sound waves are constructively interfering, right? So where the points match up, you're gonna predict that you're gonna have a higher amplitude. You're gonna hear more sound. But what happens when two sound waves destructively interfere? Is there gonna be no sound anymore? Right, let's figure that out. Let's see what happens. I would turn down your volume for this. It gets pretty annoying. So I'll give you like 10 seconds to lower your volume. I'm gonna do the same to, yeah, I would give you 10 seconds to lower your volume. So do that right now. 5 seconds. Hopefully you've lowered your volume already. 3, 2, 1. So clearly I'm hearing something. And as I move myself into certain points, you see that the volume is decreasing. Hold on, you don't actually see anything. Alright, whatever, good enough. So at certain points, you'll see that the volume is lower. Right? You'll see at certain points, if I move this person right here, you'll see the volume is lower. Because the two sound waves are destructively interfering with each other at this point in time. And if I move this person somewhere else, well, now I can hear a greater volume. And so let's see where if there's a place where I cannot hear anything. Well, there's not really a place where I can't hear anything, but you do see the volume difference. And that volume difference is because these two sound waves are interfering with each other. And this can happen in real life as well. Alright, so good enough. Good enough for the simulation. Now let's take a look at these two waves. So why do how do we explain constructive and destructive interference? Right? How do we explain these two things? Now, so in this GIF, there's one situation right here, and there's another situation right here. And so what happens is that these two GIFs are being combined. Right? So these two waves are definitely different. One is going up at the same time the other one is going down. Right? One is going up, the other one is going down at the same time. And if you were to combine these two waves, if you were to superimpose these two waves on top of each other, you would get a flat line because they're completely opposite of each other. Well, how do we know that? How do we know that? Well, if we take a look, I thought this was a GIF. Oh no, it is a GIF. Okay, whatever. So if we take a look at this green sine wave, or rather, it's not really a sine wave. I think it's like a cosine. Yeah, it's a cosine wave. Let's look at this green wave and this blue wave on right here. All right, top left. Top left. Just ignore the GIF for now. Ignore every other picture. Just focus on the top left. You'll see that these two waves are on top of each other. Well, we can explain that these two waves are out of phase. We say that waves are out of phase, right? So we say that either waves are in phase, right here on the bottom, in phase, which means they're basically the same as each other. They have the same node, right? They're starting from the same node. They're ending at the same node. They have the same antinode, right? So they peak at the same antinode. They peak at the same, well, they have the same node. And so they're in the same phase. They're in phase with each other. These two waves are in phase with each other. same node, same antinode, same node, same antinode. But when two waves have different nodes and antinodes, we say that they're out of phase. We say that they're out of phase. So both of these waves have two different nodes and two different antinodes. Well, we explained how out of phase they are by saying what kind of angle they have, right? So this right here, right? There's one up and then down. We say that it's 180 degrees. We say that's 180 degrees, kind of like a semicircle, right? A semicircle, if you take half of a semicircle, that's just completely one up, that's 180 degrees. That's one semicircle. And then you add another semicircle and then you get 360 degrees, okay? So one semicircle, one half of a circle gives you 180 degrees. And then the entire wave is 360. So that's how many degrees are in one wavelength of a wave. 360 degrees. And this wave right here, this green wave's antinode, not antinode, no, its node is at 90 degrees. Well, if the node of this green wave is at 90 degrees and this node of this blue wave is at 180 degrees, well, we can say that these two waves are 90 degrees out of phase. 90 degrees out of phase. Okay, 90 degrees out of phase because they are that much apart from one another. They are 90 degrees out of phase. Okay, so now let's take a look at this one. This gift is not too important. You'll never ever see be tested on degrees being represented as radians. But this is how you use it in greater, higher level physics. But for now, degrees is fine. But if I would represent things using radians though. That would be the proper way of representing. But for now, we can say that. Well, okay, that's you can represent it both ways. Both ways are correct. But you don't. For right now, you don't need to learn about radians. The only thing you need to learn about is in terms of degrees. So phase shift, phase shift, phase shift. So again, it's these two waves are 90 degrees uh out of phase with each other. And if we take a look at this one, clearly this orange wave and this black wave is 180 degrees out of phase with each other, right? They're 180 degrees out of phase with each other. And this fourth wave on the bottom is 0 degrees in phase with they're in phase with each other. They are in phase with each other. And this one, the third one, is 180 degrees out of phase. And so when you get two waves that are 180 degrees out of phase with each other, what's going to happen is you're going to get these complete destructive interference. You're going to get complete destructive interference. And when you get two waves completely in phase with each other, you're going to get complete constructive interference. All right, so I would look at this. I would study this picture, and I would study this picture on the right as well. Cool, great, perfect. Now let's actually go through these problems. All right. Where's my tablet driver? Tablet mode. No, that's not what I want. Folder. Oh, right here. All right, cool. Sure. Number one. Number one. So, how many antinodes are shown in this standing wave? Again, you know that. And I'm gonna draw this horizontally just so that you have a better kind of understanding. of it, right? So it's the equilibrium line. And so when we know that this is our nodes are at the equilibrium line. So there are 4 nodes here. And so the antinodes are on the maximum displacement. So these are antinodes, anti, anti, anti. And so there are 3 antinodes here. Right, so that's the definition of nodes and antinodes. So if we take a look at this picture right here, there are definitely, it's rather just, instead of being horizontally, it's vertical. Right, instead of horizontally, it's vertical. Now, that's the equilibrium line. Remember, that's the equilibrium line. Or rather, let's actually just erase this part. Okay, perfect. And this dotted line on the picture, well, that's just the opposite of it, right? So the dotted line is when the wave moves in the other direction. That's just what the dotted line means. It's just predicting the future. It's like a future line. And so you're only gonna focus on this dark bolded line right here. And so there's one antinode right there, another antinode, and another antinode. And so there are only 3 antinodes in this picture. Number two, maximum constructive interference occurs at which nodes? So no interference usually, so there are 2 waves right here. String. Usually interference doesn't happen at nodes, right? Usually interference doesn't happen at nodes. So again, so interference doesn't occur at nodes. So if you know the statement, this is a general statement. Obviously, it's not going to be true for everything, but this is a general statement you can assume for regions, right? This is a general statement. Interference occurs at nodes, doesn't occur at nodes. So B and D is completely, B and D are wrong, right? Choice B and D are wrong. Choices B and D are wrong, not the nodes. And so the only left with choice A and choice C now. Well, choice A is saying antinodes A, C, and E. Clearly, A, C, and E are nodes. A, C, and E are antinodes. Right? A, C, and E are antinodes. I mean, no, A, C, and E are nodes. I'm sorry. These are nodes. These are nodes. And antinodes are right here. Are the maximum displacement, maximum. Antinodes are maximum displacement. And so antinodes are B and D. So the only choice is C. Right? Maximum displacement only occurs at antinodes. You can do 3 yourself. It's not too hard. 4 is something you can do. 5. And so we talked about this in the GIF. You saw this. So 5 is saying what will happen as he pulses me and are superimposed. There's a typo there. It should say superimposed. The maximum displacement of the medium is what? Well, you kind of look. Well, the GIF showed it. Hold on. Right, this GIF showed what happened. If you have these 2 waves and they combine, they hit with each other, they combine. Right, their amplitudes combine. And so the amplitude of pulse A is 3 centimeters. And the amplitude of pulse B is 3 centimeters as well. Well, if they combine, once they come in contact with each other, what is the combined height of these 2 waves at the maximum displacement? Okay, so that one you can answer yourself. What's 3 plus 3? Come on, you guys can do that. I believe in you guys. 6. What waves are in the region between points A and B? They will undergo what? All right, so what the problem is saying is, so you have this wave right here, right? And then you have an identical wave. These are two identical waves, right? They're not different, they're identical. So what is going to happen when you superimpose? Hold on, give me a second. And so what's going to happen when you superimpose this wave right on top of this wave, right? So what they're saying is they're going to put this wave, this second wave, right on top of the first wave. So if they put it right on top of the first wave and they're both identical, they're both in phase, what's going to happen? Well, they're definitely not going to cancel each other out. They're going to constructively interfere. They're going to become an even larger wave, right? They're going to become an even larger wave. Oh man, that looks dirty. So constructive interference. Constructive interference, right? So they're going to constructively interfere with each other because they're the same. They're waves in phase. They're in phase. Both waves are in phase with each other. So 7. Which 2 points is constructive interference occurring? This one I can. Okay, so I'll give you a hint for 7. After I give you hints for 7, it should be fine. Just a reminder, the trough is the maximum displacement going down, and then the crest is the maximum displacement going up, right? So what happens when you combine crest and crest? And what happens when you combine crest and trough, right? So crest and crest should constructively interfere, right? There's constructive interference here if you combine crest and crest. And if you combine crest and trough, you're going to get destructive interference. So the question wants, at which 2 points is constructive interference occurring? You can answer these 2 questions based on what? Based on the hints I gave you. 8. 8 is something you can do as well. You're basically just using addition or subtraction because you want the greatest positive displacement. 9 is the same thing. You're basically combining these 2 pulses. 10 is the same thing as well. 10 is the same thing. 11. So which points on this wave diagram below are 90 degrees out of phase with each other? So again, out of phase. Out of phase. So let's actually draw this first. So again, if you don't want to refer back, this is 100. That's actually not 180. I'm sorry. This point right here is 360 degrees. This point is right here is 180. This point right here is 0 degrees. This is 270, right? And this should be 90 degrees. So again, if you were to take a circle, right? Half a circle. A full circle is 360. A full circle is 360. Half a circle is 180. All right, so that's how you can think of it. That's how you can think of this wave. And so they want to know which 2 points are completely are 90 degrees out of phase with each other. So that's actually no. This is C, right? No, it's not C. So you can draw this to help yourself, right? You can draw this to help yourself. And that's E, this is D, and this is C. So again, this is 0, this is 90, this is 180, this is 270, and this is 360. So let's look at choice A. Choice A says A and E. A and E are in phase. Why are in the phase? Because if you just start here again, well, that's also 0 degrees, right? 0 degrees, 360, 0 degrees, 360. You're basically starting at the beginning. You're basically, if you were to go around in a circle, you started here at 0 degrees and you go around in a circle, and then you end up back at that dot, well, you're in phase. You're in phase with each other. So A and E are in phase with each other. You're basically starting at the beginning there, so that's why. B and C are also in phase with each other. They're both at 90 degrees, right? They're both at the same exact point and same exact height, so they're both in phase. C and D are definitely not in phase. C and D are at opposite points, right? C and D are opposite points. Well, how much out of phase are they? They're 180 degrees out of phase. So C and D are 180 degrees out of phase. What about D and E? D and E, well, we want 90 degrees out of phase, not 180 degrees. Well, let's look at D and E. Well, D is at 270 and E is at 360. So yes, the phase difference is 90 degrees out of phase. So choice D is the correct answer. You would apply the same logic to 12 based on what I did here. You would use this example. It's actually the same exact logic. 13 uses the same exact logic. 14 uses the same exact logic, right? You want something in phase. I would be careful about choosing whether or not it's B or C. You have to think about it, right? Think about it in terms of a circle or this wave that I drew right here. 15, same thing. 15, same thing. 16, same thing. You would use this. No, none of the questions seem out of the ordinary. All right, good stuff.